I think it's time to start now. Good morning, good evening for everyone. Today we will continue our Europe and non-associative algebra seminar. Today's speaker is Ramón González Rodríguez from the University of Vigo. He's going to talk about quasigroupoids and weak Hopf quasigroups. Please.
Okay, thank you very much for the introduction, and also I would like to thank the organizers, and especially to Ivan Kaidogorov for the invitation to give a talk in this seminar. Well, the main topic of the talk will be to present the definition and the most relevant properties of two non-associative algebraic objects. These objects are quasigroupoids, where for us quasigroupoids will be the non-associative version of groupoids, and weak Hopf quasigroups. In this case, we are considering the non-associative version of weak Hopf algebras. All the results of this talk can be found in the following 4 papers. The last one is in press, and all of them are accessible in archive. Well, taking this into account, the outline of the talk will be as follows. In the first part of the talk, we will present the monoidal context in which the theory will be developed, as well as the necessary basic notions. In the second and the third sections, we will introduce the definition of weak Hopf quasigroup with his main properties. For example, in the third section, we will see that these objects can be characterized as in the case of Hopf algebras using the associative Galois morphisms. The fourth part of the talk is dedicated to presenting the notion of quasigroupoid and the main properties of this object. And in the fifth section, we will show that the categorical, that there exists some categorical relationships between the category of weak Hopf quasigroups and the category of quasigroupoids. And finally, in the last part, we will see how using matched pairs of quasigroupoids, we can construct new quasigroupoids. Then, for us, in the talk, see the notes a braided monoidal category with a tensor product denoted by this symbol and unit object chi. And with the little c, we will denote the braiding of the category. And remember that a monoidal category is a category C equipped with a tensor product functor, that is this one, an unit object, and a family of natural isomorphisms, A, R, and L. Call it associativity, right unit, and left unit constructs, respectively, and satisfying 2 axioms, the pentagon axiom and the triangle axioms. In these equalities, AD of X denotes the identity morphism for every object X in the category C. Also, if C is braided, if for any couple MM of objects in the category, there is a natural isomorphism denoted by this, satisfying the hexagon axiom. Then for any object M, N, and P in C, these 2 following identities hold. Okay. It's well known that every non-street monoidal category is monoidal equivalent to a street one. In the street case, the constraints are identities, and then we can assume without loss of generality that the category is a street. As a consequence of this fact, the results contained in the talk remain valid for every non-street braided monoidal category. Also, we will assume that in this category, every idempotent morphism Q in C splits, then C is Cauchy complete. And this means that if Q is an idempotent morphism, then we have an object theta, call it the image of Q, and 2 morphisms, I and P. I is a morphism between the image of Q and I is the injection, and P is the projection, a morphism between I and the image of Q, satisfying that the composition of P with I is Q, and the composition of I with P is the identity of the image of Q. For example, there are interesting examples of categories satisfying this condition, for example, a category with epimonic decomposition, or categories with equalizers, or categories with coequalizers. Also, for simplicity of notation, if we have three objects, B, U, and M in the category C, and a morphism F between B and U, with M tensor F, we will denote the tensor product of the identity of M with F, and similarly, F tensor M denotes the tensor product of F with identity of M. An algebra, an unital magma in the category C is a triple where A is an object in the category, eta of A is the unit morphism, and mu of A is the product, satisfying this identity. If we have the associativity condition, that is this equality, then we will say that the unital magma is an algebra. For two unital magmas or algebras, A and B, a morphism between them in C is a morphism of unital magmas if F preserves the unit and F is multiplicative in this sense. In a dual way, a counital comagma is an object in the category with a morphism between C and K, the counit morphism, and a comultiplication or a coproduct morphism, delta of C between C and C tensor C, satisfying this first identity. And if we have the co-associativity condition, that is this identity, we will say that the counital comagma is a coalgebra. As in the case of unital magmas, if we have two counital comagmas or two coalgebras, a morphism between them, C is a morphism of counital comagmas if F preserves the counit and F is comultiplicative in this way. For any counital comagma or any coalgebra, we will say that D is co-commutative if we have this identity, or the composition of the coproduct with the braiding of the category is the coproduct. And finally, in this first point, if we have two morphisms between a counital comagma C and a unital magma A, with this symbol, we will denote the convolution product that is defined by the composition of these three morphisms. The coproduct, the tensor product of the two morphisms, and finally, we compose with the product on A. Then, for introduce the notion of Hopf quasigroup, first we need to speak something about the notion of weak non-associative bialgebra in the category C. A weak non-associative bialgebra is a unital magma and a coalgebra satisfying these three axioms. The first one is the usually compatibility condition that we can find, for example, in the definition of Hopf algebra. And in the second point, we have the identities involving the product with the composition of the counit. And in the third point, we have the identities for the unit and the coproduct. For example, in this definition, if we assume that the product is associative, then the previous notion is the one of weak bialgebra in a braided monoidal category. If the product is associative and the counit and the coproduct are algebra morphisms, then we have the notion of bialgebra, the usual notion of bialgebra in a braided monoidal category. And for example, if the counit and the coproduct are morphisms of unital magmas, we have the notion of non-associative bialgebra in a braided monoidal category. Then, taking this into account, what is a weak Hopf quasigroup in the category C? A weak Hopf quasigroup in the category C is a weak non-associative bialgebra for which exists an endomorphism of H that we call the antipode, as in the case of Hopf algebras, and such that if we denote by pi LH the target morphism defined by this, by pi RH the source morphism defined by this, all these equalities hold. In the first one, we have that the target morphism is the convolution product of the identity and the antipode. In the second point, we have that the source morphism is the convolution of the antipode with identity. In the third point, we have that these two convolutions products are exactly the antipode. And finally, the points 4, 5, 6, and 7 are the qualities involving the product of the Wyckoff Quasigroup with the morphism pi R and pi L. For example, particular instance of this definition. If the product defined in H is associative, then this one is the definition of weak-braided Hopf algebra introduced by us in this paper. If the product is associative and C is the category of vector spaces over a field K, Wyckoff quasigroups are exactly Wyckoff algebras as was defined by Gabriel Avon, Florian Neal, and Cornel Eslachangi in this paper. If the product is associative and the counit and the coproduct are morphism of algebras, then we have the usual notion of Hopf algebra in a braided monoidal category. And finally, if the counit and the coproduct are morphisms of unital magmas and C is the category of vector spaces, we get the notion of Hopf quasigroup introduced by Jennifer Klim and Klim and Majid in this paper. And this last notion of Hopf quasigroup in our braided setting is the following. A Hopf quasigroup in the category C is an unital magma and a coalgebra such that the counit and the coproduct are morphisms of unital magmas, and there is an endomorphism of H, lambda of H, that we call it the antipode of H, satisfying these four identities. For example, a particular instance of this definition is the case of C, the category of sets. In this case, a Hopf quasigroup in C is exactly a loop with inverse property, an AP loop. An AP loop, remember that an AP loop is a set with a product, an identity, and with the property that for every element on L, there exists an inverse satisfying these two identities for all B in L. And note that in this example, we have the co-commutativity condition because in this case, the coproduct is the usual duplication. Well, for any weak non-associative algebra, we can define two new endomorphisms of H. The first one is the overlying L, or the overlying target, is defined by this composition. And also we have other morphism that is the overlying source, that is definition for this composition. And in our setting, for any weak non-associative algebra, it's possible to prove that the target, the source, the overlying target, and the overlying source are examples of idempotent morphisms. And also, it's possible to compute, as in the case of Wyckoff algebras, all the compositions between these four idempotent morphisms. And then we have all these identities between the compositions. And in a more general setting, for any weak non-associative algebra, we can assure that any equality containing the idempotent morphisms defined previously, the coproduct and the counit that holds for Wyckoff algebras also holds for H. For example, this is a little list of identities that holds for Wyckoff algebras, and we can assure that all these identities can be proved for the non-associative setting of weak non-associative bialgebras. But we have more because for any weak non-associative bialgebra, if we denote by HL the image of the target morphism, by pi L the associated projection, and by L the associated injection, then this first diagram is an example of an equalizer diagram, and this other diagram is an co-equalizer diagram. And then taking this into account, the image of the target morphism with this unit and with this product is an unital magma in the category C, And also we can prove that the same object with this co-unit and this co-product is also a coalgebra in C. In any case, we also can to prove that for any weak non-associative bialgebra, we have these three identities. And these three identities implies that the unital magma that we defined in the previous slide for the image of the target morphism is an algebra in the category C. This implies that the restriction of the product to the image of the target morphism is associative. And also we have the same for the image of the source morphism. Using a similar results, we can prove that the image of the source morphism is an algebra in the category C. If we assume that we are working with a weak Hopf quasigroup, then we have an antipode, and the antipode is possible to prove that it's unique and leaves the unit and the co-unit invariant. And also we can compute all the composition of these antipodes with the source morphism, with the target morphism, with the overlying source morphism of the overlying target morphism. And finally, the more interesting result is the following. If H is a weak Hopf quasigroup, the antipode of H is antimultiplicative and anti-comultiplicative. Then we have these two equalities. What is a morphism between weak Hopf quasigroups? We have two weak Hopf quasigroups, and also F is a morphism in the category C. Then this morphism in the category C is a morphism of weak Hopf quasigroups if it is a coalgebra morphism and satisfies these four identities. The identities 1, 2, and 3 are the identities that involves the morphism F with the source and the target morphism. And the more relevant identity is this one, because this identity says that the F is multiplicative, but if we compose with this morphism nabla of H. And this morphism nabla of H is an endomorphism of H tensor H and is defined by this composition and is an idempotent morphism. Then if we work in the associative setting, this definition is exactly the one introduced by Gabriel Abón, José Gómez Torrecillas, and Esperanza López Centella for the category of weak Hopf algebras. In our case, and in the following, with this, we will denote the category of weak Hopf quasigroups. And as a brief resume, setting the associativity, we can say that weak Hopf quasigroups satisfy the relevant equalities that we can find in the theory of weak Hopf algebras. And one of them, for example, is the characterization of weak Hopf quasigroups using the Galois morphisms. In the case of Hopf algebras, we have a characterization of the condition of Hopf algebra using these morphisms. Suppose that H is an algebra coalgebra in the category C, then we can define the right Galois morphism beta by this composition, and also we can define the left Galois morphism gamma by this other composition. Sorry? Yes, by this other composition. Then we have a theorem that says the following. If H is a algebra, then the following assertions are equivalent. H is a Hopf algebra, the right Galois morphism is an isomorphism, and the left Galois morphism is also an isomorphism. And the proof for 1 implies 2. If we have that H is a Hopf algebra, we can define the inverse of beta by this composition, and for 2 implies 1. It's possible to obtain the antipode for the bialgebra by this other composition, where here we have the inverse of the antipode. Then the aim of this section is to prove that in the case of weak Hopf quasigroups, we have a similar result. But previously, we need to introduce some morphisms. And the first one are the omega morphisms. Suppose that H is a weak non-associative bialgebra. And then it's possible to define 4 morphisms, omega 1L, omega 1R, omega 2L, and omega 2R. And these four morphisms are idempotent. And as a consequence, we have these four objects that are the image, the corresponding image of these idempotent morphisms. And with Q, we will denote the associated projections, and with J, we will denote the associated injections. And then we have these two identities for any sigma in LR or any alpha in 1, 2. Then, using the image of these idempotent morphisms, we have that in this setting, for any weak non-associative bialgebra, these two diagrams are co-equalizer diagrams, and these two diagrams are also equalizer diagrams. If H is an unital magma, we say that a morphism, an endomorphism of H tensor H is almost left H linear if phase satisfy this identity. Also is almost right H linear if satisfy this other identity. And by dualization, for a counital comagma, we will say that a morphism C is almost left H collinear if satisfy this identity, and A is almost right H collinear if we have this other identity. Then, working with the Galois morphisms and the omega morphisms, we have examples of this kind of morphisms, because for any unital magma and counital comagma, the right Galois morphism vita is almost left H linear and almost right H collinear. The left Galois morphism gamma is almost right H linear and almost left H collinear. And for the omega morphisms, we have the following. The omega 1L and the omega 1R are almost left H linear and almost right H collinear morphism. And the morphism omega 2L and omega 2R are almost right H linear and almost left H collinear morphisms. Moreover, if H is a Hopf quasigroup and then we have an antipode, we can express the omega morphisms as compositions of the previous Galois morphisms in the following way. The omega 1L is the composition of beta with overlined beta, where overlined beta is this morphism. The omega 1R is the composition of overlined beta with beta. Sorry. The omega 2L morphism is the composition of overlying gamma, where overlying gamma is this morphism with gamma. And the morphism omega 2R is the composition of gamma with overlying gamma. If, moreover, the weak Hopf quasigroup is a Hopf quasigroup, then in this case, the four idempotents are trivial in the following sense, are equal to the tensor product of the unit with the co-unit. And then in this situation, the omega morphisms are all identities. And as a consequence, we have that in this case, the Galois morphism beta and gamma are isomorphisms with inverses overlying beta and overlying gamma respectively. Then we have here the main result of this point. Suppose that H is a weak non-associative bialgebra, then the following assertions are equivalent. H is a weak Hopf quasigroup, and the morphism F defined by this composition, where here we have the morphism beta, and G that is defined by this other composition are isomorphisms, and the morphism defined by this other composition is almost left H linear, and this other morphism defined with the composition with inverse of G is almost right H linear. The proof is similar to the case of Hopf algebras because, for example, for 1 implies 2, the definition of the inverse of F is this one, where here we have the overlying beta morphism, and for the definition of the inverse of G, we have this other composition with the overlined gamma morphism defined previously. And in the other side, we can construct the antipode of H by the composition of this new morphism with the unit and the counit. And here we have the inverse of F. In the case of Hopf quasigroups are particular cases of with Hopf quasigroups. In this case, we have the following corollary. If H is an unital magma and a coalgebra such that the counit and the coproduct are morphisms of unital magmas, then H is a Hopf quasigroup if and only if the Gaussian maps beta and gamma are isomorphisms and they have almost left H linear and almost right H linear inverses, respectively. Okay. For example, this result was proved by Thomas Berzinski for Hopf quasigroups in the category of vector spaces over a field K in this paper. And if we think in the main theorem of this point in the associative setting, we have the following. Suppose that H is a weak bialgebra, then the following are equivalent. H is a weak Hopf algebra. This morphism F is an isomorphism of this other morphism G is an isomorphism. Then this is the result proved by Peter Sarenburg for weak Hopf algebras in the category, also in the category of vector spaces over a field K in this other paper. Well, then we have the main properties for weak Hopf quasigroups, and the next point is to speak something about the notion of quasigroupoid. And for to speak the notion of quasigroupoid, first we need to introduce some notation. If we have three sets, X, I, and zeta, and two morphisms alpha between X and zeta and beta between I and zeta, with this we will denote the pullback of alpha and beta. Then this set is the set of pairs xi in the Cartesian product of x with I such that alpha x is beta I. Well, what is a quasigroupoid? A quasigroupoid or RIP lupoid is an ordered pair of sets A0, A1 such that there exists three maps SA, TA, and identity of A, call it the source, target, and identity respectively, satisfying this identity for all X in A0. Also, we have a product map that is defined in the pullback of the target and the source morphism on A1, defined by this, and a map lambda of A between A1 and A1, call it the inverse map, such that for any A in A1, we have this identity. Also, for any pair of in the pullback of the target and the source morphism, we have these identities. And for any pair in the pullback, this pair and this pair are also in the pullback, and then we have these two identities. In the following, the set A0 will be called the base set, or also the set of objects of A, and the set A1 will be called the set of arrows of H. And we will say that quasigroupoid is finite if his base set is finite. For example, in the case of A0 equals to 1, the notion of quasigroupoid is exactly the notion of loop with inverse property. If the product of the quasigroupoid is associative, then we have an usual groupoid, and then we have a category where every idempotent morphism is an isomorphism. And finally, this notion of quasigroupoid is exactly the one of inverse semilupoid satisfying the unities associative assumption. And this notion was introduced by Grabowski in this paper. Then, directly from the definition, we can prove all these identities involving the source, the target, and the inverse map for any A in the set of arrows and any pair AB in the pullback. And what is isomorphism between quasigroupoids? Suppose that we have two quasigroupoids, a morphism or a quasigroupoid morphism between them is a pair of maps where gamma 0 is a map between the set of objects, and gamma 1 is a map between the sets of arrows, satisfying this identity for the source maps, this other identity for the target maps, this identity for all x in the set of objects for the identities, and the multiplicative condition for any pair in the pullback. Then we will denote by this the category of quasigroupoids, because it's obvious that the composition of two quasigroupoids morphism is a quasigroupoid morphism. And with this other notation, we will denote the full subcategory of the category of quasigroupoids whose objects are finite quasigroupoids. Examples. Suppose that we have a loop with inverse property with this product, and suppose that X is a set. And assume that there exists a map phi of X between this Cartesian product and X, satisfying these two conditions for every X in X and IB in A. Then, under these conditions, it's possible to construct a quasigroupoid, an example of quasigroupoid. In this case, the quasigroupoids will be denoted by B, and the set of objects is X. The set of arrows is the Cartesian product of A with X. Here we have the source map. This one will be the target map, and this is the identity map. This set is the corresponding pullback, and in this pullback we define the product by this, and with this we define the inverse map. As was proved by us in this paper, it's possible to obtain examples of this kind of quasigroupoids working with mode-found loops of a small order and the four-dimensional Hopf algebra example. The second example is the following. Suppose that A is a loop with inverse property, and suppose that X is a set, and denote by T the set of these triples where A is in A and X and I is in X. Then the quasigroupoid T is defined in the following way. The set of objects is the set of this triple, and the set of arrows is T. With this, we have the source map. This one is the target map, and here we have the identity. In this case, this set is the pullback set, where we define the product of the quasigroupoid, and the inverse map is defined by this. The third example is an example where A is a quasigroupoid, P is a set, and pi between P and the set of objects of the quasigroupoid A is a surjetive map. Then it's possible to define a new example of quasigroupoid where the set of objects is P, the set of arrows is the set of these triples, satisfying these two identities. This one is the source. Here we have the target map, and the identity is defined by this. This is the pullback set in this example, where we can define this product. This is the product of the quasigroupoid. And finally, this is the inverse map for this quasigroupoid. On the other hand, suppose that K is a field, and suppose that you have a finite quasigroupoid. Then the quasigroupoid magma, denoted by K of A, is defined by the free vector space in this way, and the structure of quasigroupoid is the following. It's a co-commutative weak Hopf quasigroupoid with this unit, with this product defined by the product of the quasigroupoid if the pair AB is in the pullback and 0 in other case. This one is the counit. Here we have the coproduct, and the antipode is defined thanks to the existence of the inverse map. And if we work with morphisms of finite quasigroupoids, we can obtain an morphism of Hopf quasigroupoids between the quasigroupoids magmas using the linear extension of the map gamma 1 between the set of arrows defined by this. Then this implies that we have a functor that we will denote by this, the Hopf quasigroup functor, that for every finite quasigroupoid we have a Hopf quasigroup, a cocommutative Hopf quasigroup defined by this. And for the morphisms, we have this. Then in the next point, we will to show that under some conditions, it's possible to find other functor, but in this case, between the category of Hopf quasigroups and the category of finite quasigroupoids. Then in this case, C will be the category of vector spaces over a field K. And then for any set X with K of S, we will denote the free K vector space on S, defined by this. And this vector space is usually called the group-like coalgebra, and the structure of coalgebra is the usual. This one is the counit, and this one is the coproduct. For any coalgebra in this category of vector spaces, we will say that an element G is a group-like element. It is satisfy these two conditions. And with G of D, we will denote the set of group-like elements on D. It's very easy to prove that in this setting, the set of group-like elements is an example of subcoalgebra of D. For example, if S is a set and we compute K of S, then the set of group-like elements of K of S is X. Well, then suppose that we have a wave of quasigroups and consider an element T in H satisfying this condition of group-like element. Then we can prove the following. All these products are T. These four elements are idempotent elements in H. Also, we have this identity for the image of T using the target morphism and using the source morphism. Also, we have these identities for the composition of the target of the source morphism on T. These equalities that say that says that in T, the target in T is the same that the overlying target in T and the same for the source morphism. And also using 5 and 3, we have these two identities for T. And finally, in 7 and 8, we have the expressions of the compositions of the antipode with the target and the source morphism on T, and the same for the square of the antipode. And finally, for a T satisfying the previous condition, we have that the square of the antipode on T is exactly T. And this is these are the relevant identities to construct the functor. Because using these identities, we have the following. If H is a Hopf quasigroup and G is a group-like element of H, then the image of G by the target and the source and the antipode are also group-like elements. On the other hand, in this setting, the algebras HL and HR, the image of the target and the image of the source, are inseparable, finite dimensional, and semi-simple. And the more relevant thing in this case is the following. All the group-like elements of H are, of course, linearly independent, and the cardinality of the set of group-like elements of H in intersection of the group-like elements with the image of the source morphism, the cardinality of these sets is finite. Then, using this last property, we have the following theorem. Suppose that H is a weak Hopf quasigroup. Then we can define this ordered pair of sets. The first one is the intersection of the set of group-like elements with the image of the source morphism. And the second one is the set of group-like elements. Then this pair is a finite quasigroupoid where the source is defined using the source morphism, the target is defined using the target morphism, and the identity is obviously the identity. The product is defined using the product in the quasigroupoid H, and the inverse map is defined using the antipode of the weak Hopf quasigroup. And this construction works well for morphisms, because if we have a morphism of weak Hopf quasigroups, this pair defined in the set of objects by this, by F on R, I define and define it in the set of arrow by this as F of G, is a morphism of quasigroupoids between the quasigroupoids T of H and T of H prime. And then as a consequence of this fact, we have and we can prove that there exists a functor that we will call the quasigroupoid functor between the category of weak Hopf quasigroups and the category of finite quasigroupoids defined by T of H in the objects and in the arrows. And this functor, the weak Hopf quasigroup functor, is left adjoint of the quasigroupoid functor. Then we have an adjunction in this setting of the category of vector spaces. But we have more, because these two functors induce an equivalence of categories between the category of finite quasigroupoids and the full subcategory of weak Hopf quasigroups of all pointed cosemisimple weak Hopf quasigroups. And if K is algebraically closed, these functors induce an equivalence between the category of finite quasigroupoids and the full subcategory of weak Hopf quasigroups of all Q-commutative cosemisimple weak Hopf quasigroups. For example, in the associative setting, these two results are the results proved by Gabriela Bon, José Gómez Torrecillas, and Esperanza López Centella in this paper for weak Hopf algebras. But if we think in the category of Hopf quasigroups, as a corollary, we have that the category of loops with inverse property is equivalent to the one of pointed cosemisimple Hopf quasigroups. And also, if K is algebraically closed, the category of loops with inverse property is equivalent to the one of Q-commutative cosemisimple Hopf quasigroups. And this one is the proper generalization of a classical results of Hopf algebras and groups that says that the category of group is equivalent to the one of pointed cosemisimple Hopf algebras. And if K is algebraically closed, the category of groups is equivalent to the one of co-commutative cosemisimple Hopf algebras. Well, then we have weak Hopf quasigroups, quasigroupoids, and then the last point of the talk is the point for the matched pairs of quasigroupoids. Then first we need to speak something about actions of quasigroupoids. Suppose that A and H are two quasigroupoids with this product and this product respectively, and with the same base. Then a left action of H on A is a map defined in this pullback to A1 and satisfying these three conditions. And in a similar way, we have the notion of right action. In this case, we need a right action of A on H is a map phi of H defined in this pullback, in the same pullback as in the previous one, and satisfying these three identities. And then with this left action and the right action, we can introduce the notion of matched pair of quasigroupoids. A matched pair of quasigroupoids is a pair of quasigroupoids with the same base together with a left action of H on A, denoted by phi of A, and a right action of A on H, denoted by phi of H, and satisfying these properties that we have here. As a consequence of this definition, it's possible to obtain many interesting identities for matched pairs of quasigroupoids. And for example, this is a little list of some of the identities that we can prove for any matched pair of quasigroupoids. The interesting thing of the matched pairs of quasigroupoids is that permits to construct new quasigroupoids. Because if we have a matched pair of quasigroupoids, this pair, where the set of objects is the set of objects of A0, and the set of arrows is this pullback, is a quasigroupoid where the source morphism is defined by the source morphism of H, the target morphism is defined by the target morphism of A. This one is the identity map, or the identity map. Here we have the product, where C is a map between these two pullbacks, and the components of this map phi are, this one is the first component, and this other one is the second component. And the inverse map is defined by this. If A8 is a matched pair of quasigroupoids, then this new quasigroupoid that we construct in this theorem, we will call it the double cross product or the diagonal quasigroupoid of A and H, as in the case of Hopf algebras. For example, suppose that A is a loop with inverse property with this product and X is a set, and assume that there exists an action of A over X denoted by phi of X. Then B is the quasigroupoid constructed in the previous slide and is the quasigroupoid associated to the action phi of X, and denotes with XD the discrete groupoid. Then this pair is a matched pair of quasigroupoids where here we have two actions. This is the set of objects, the set of arrows. This one is the source map. Here we have the target. This one is the identity. The product is defined by this, and this one is the inverse map. For any matched pair of quasigroupoids, the two quasigroupoids A and H are subquasigroupoids of the double cross product. This morphism I of A, defined with these two components, are the first inclusion, the inclusion of A in the double cross product, and similarly for H, with this we denote the inclusion of H in the double cross product. This is the components of this inclusion. Well, then in the theory of groups, or in the theory of Hopf algebras, there is a close connection between matched pairs and exact factorization. And in this case, we have the same properties. Suppose that A, H, and B are quasigroupoids with the same base. Assume that A and H are subquasigroupoids of B with these two associated inclusions, and such that the first components are the identity of A0. And suppose that diamond is the product defined in B. Then we will say that this pair is an exact factorization of B if, in the case that the products involved are defined, we have these 6 identities, and also the map theta of B defined by this composition is abjection. The relevant result in this part says the following. If we have an exact factorization of a quasigroupoid P, then there exists a matched pair of quasigroupoids AH and an isomorphism of quasigroupoids between the double cross product of A and H and B. This result is a generalization of a classical result that we can find in the theory of groups, or for example, in the theory of Hopf algebras. But we have more, because for any matched pair of finite quasigroupoids, suppose that phi of A is the left axiom of H on A, and phi of H the right axiom of A on H, then we can define two morphisms in the category of vector spaces over K by this. The first one is defined by the axiom of H on A for any pair in this pullback and 0 in other case. And the second morphism is defined by the axiom of A on H if HA is also in this pullback and 0 in other case. Then, using these two axioms, we can define this new morphism phi by this composition, and also we can define this other morphism nabla of phi by this other composition. And the expressions on elements of these two morphisms are the following. For phi in H tensor A is exactly this tensor product if the pair is in the pullback and 0 otherwise. And nabla of phi is the identity if AH is in the pullback and 0 otherwise. Then, if this is the form of nabla of phi, we have that nabla of phi is an idempotent morphism with and the image generated by these elements. And then if we denote by this, the image of this morphism nabla of phi, this is a K vector space with a product defined by this composition, and the form of this composition on elements is exactly this tensor product if the pair HB is in this pullback and 0 otherwise. Then, for any matched pair of quasigroupoids, the vector space defined in the previous slide is a co-commutative Hopf quasigroup with this unit, with the product defined also in the previous slide, and where for all null element in the vector space, the co-unit is defined by this, the coproduct is defined by this, and the antipode is defined by this expression. Then, for any matched pair of finite quasigroupoids, the co-commutative Hopf quasigroups K of H of the double cross product of A with H, and this new Hopf quasigroup defined in the previous slide is in the category of Hopf quasigroups. And in that loops with inverse property are particular cases of this situation, pues these two co-commutative Hopf quasigroups, this one and this one, are also isomorphics in the category of Hopf quasigroups. And then that's all. Thank you very much for your attention.
Thank you, Ramon. Is there any questions? Maybe some questions by chat? No? Any comments?
Can I?
Yes, please.
In your theorems about matched pairs, there was the quasigroupoid finite. This is a strong restriction, or can be also for non-finite case to.
For non-finite, it's not possible to obtain the results because it's impossible to obtain the unit. This is the problem. Because in the unit, you have an infinite sum if you don't assume that the quasigroupoid is finite.
And here in the corollary, then the loop also finite, this inverse property loop.
what? Sorry.
In the next, yes.
In this one.
Yes.
Yes. Here are loops with inverse property, and this in this case are also finite because in this case there are one unique element in the set of objects.
Yes, yes. Thank you.
Thank you. Are there any questions? If there is no question, let's thank speaker again. Thank you.
Thank you.
And so see you in the next seminar.
No.
Thank you for all.
Thank you.
Thank you.
Okay, bye.
Okay. See you.
See you next time.